So we're here to talk about Kotlin code generation. And usually when Kotlin is presented as something you would want to try, we put up slides like this where hundreds of lines of code gets collapsed down into 4 or 5. And we tend to refer to this as boilerplate reduction. You can also think of the entire language of Kotlin as like a bytecode generator, going from our Kotlin syntax to Java bytecode. And we tend to almost trivialize that as syntactic sugar, but really it's itself kind of a mechanism of code generation, and it allows us to operate at a higher level of abstraction when we're writing the code. And for the rest of this talk, we are mostly going to focus on Java bytecode as the destination for the Kotlin language, but we're actually going to cover some of the multi-platform stuff at the end. So code generation using Kotlin, or actually in general, is a bit of both the syntactic sugar elimination and also boilerplate reduction. And it can be from almost anything. So a common example would be protocol buffers, where you define like a byte representation. You could use a different language that already exists and generate code based on, say, SQL queries. If you have API definitions that are shared between your client and server, you can automatically generate client code. If you have layouts, say, for Android, we can generate bindings so that you get the type-safe stuff automatically and don't have to deal with find view by ID. Maybe you have config files that you want to generate constants from. If you're an annotation processor where you're kind of parsing Java code, or you have a language that has an AST, or anything. The whole point here is that it doesn't matter really what the source is, just that code generation itself can come from anything and create a more usable thing to actually interact with.
So to illustrate this a little bit more clearly, we're going to go into one example, which is protocol buffers. So Square has a library called Wire, which is a code generation tool for protocol buffers. A protocol buffer looks something like this. This is the definition of what the proto looks like. So in this case, we have an ogre type, and it has 3 attributes: name, layers, and swamp. And it's already telling us a little bit about the type system, so what the generated code might look like if something is required or optional, that might be the nullability, as well as the actual type itself, so like strings. And so right now, what Wire is generating is something that looks like this. So a Java class. You might already notice that there are things here that can be easily Kotlinified. So one of them is these constructor parameters that are then being used as fields. In Kotlin, these can just be represented as constructor properties. Additionally, these 2 separate constructors can be condensed into one, because in Kotlin, you can provide default values for constructor parameters. So here, where we had to overload, we can just use a single constructor. Kotlin also gives us some things that we couldn't do before in Java. So for example, in Wire, we have to use this internal immutable copy of a list. So at runtime, we can enforce immutability of the list. But in Kotlin, you can expose just the list type, which is a read-only list type. So as long as they're not casting it to a mutable list, then they won't be able to change it. So again, we're moving stuff from runtime to more at the compiler level. The other thing is the nullability that we had in the proto file has sort of been lost here. Name should be non-null, but swamp is optionally nullable. So if we take this entire file, and instead of doing Java code generation, which is what Wire does right now, we can instead do the Kotlin code generation. Then we end up with this file, which is a lot more concise. But more importantly, we were able to take some of those runtime restrictions and make them compile time restrictions, which is just going to be a benefit to the people who are using your code. Now, one thing to note here is that the API has actually changed for people who are using this from Java. Because to access properties from Java, you're calling the getter method that backs the property instead of accessing the property directly. There is an annotation, JVM field, which you can add to the property so that from Java, it can be accessed as a field. So in order to keep the API the same, you want to add this annotation, which is sort of the first important thing when you're doing Kotlin code generation that you should be wary of, is that the API from Java is also still sane.
So the next part of the generated code is the equals hashcode and toString boilerplate. This code is currently written in Kotlin, but as we know, or as you may have seen, Kotlin has something we can add to our class to get these implementations of equals hashcode and toString generated for free, and that's the data modifier. But this ends up introducing a slight problem in this example, because we have a constructor parameter with a default value that was only being passed to the superclass. And we actually might not want to include that in the equals hashcode and toString code. So we can try and make it a property, but then it's forced to participate in those. And so you may actually be changing the semantics of equals and hash code in contrast to the code that was in Java. So the important thing to note here is that the economics of code generation is very different from when you're writing Kotlin code in the IDE. It should be thought of as OK to actually generate those boilerplate methods because it's not the user that's writing them, and you wind up with the more correct semantics. So you get all the benefit by moving that work into the code generator. And even though it's not exactly the code that you would write if you wrote it manually, you get the correct semantics.
And the final major thing that Wire is going to generate for us is this builder class, which from the Java side is what makes it really easy to compose the type, possibly leave out different values. So the nice thing about this is that you can enforce restrictions when you're actually creating the type. So in this case, there are two restrictions that we're enforcing. One of them at the bottom there is where we're saying that the name has to be non-null. And the other one is just checking to make sure that the actual values in the list are non-null themselves. These are, again, things that we can move into the constructor with Kotlin, and they also become compile time. Similar to what we were doing before with the constructor properties, we can take these restrictions that were part of the builder and instead put them in the constructor. And so that's going to look something like this, where now we have the default value for the list as well. And you can only call this constructor with a name. You're never going to be able to call it without a name. So those restrictions that were at first part of the builder can now be part of the constructor. And the nice thing about Kotlin is that when you call a constructor or any method, you can, the actual parameter names themselves are sort of part of the API. So one of the great things about the builder pattern in Java is that you're calling it in a way where it's clear what every single value is being used for. So in this case, there are two strings, right? The name and the swamp. If we didn't have the parameter names here, it might not be clear which one is which. But with Kotlin, because this is part of the API, it still looks really clean. From Java, though, it's not as nice.
Yeah, so the advantage of the builder pattern is that it allows you to supply a subset of the arguments, and that's any subset. So there's an annotation called JVM overloads, which will actually allow Java consumers to consume the constructor parameters kind of in order in these different variants. But if you need to supply a subset that's not created by this code, you're out of luck. And the other disadvantage from the Java side is that we lose that named, the ability to actually have a name associated with the value. So we're supplying 3 arguments to this constructor, but it's not really clear what they correlate to.
So this is part of a larger topic with Kotlin, which is the Java interop. And I think there are important things to point out specifically for code generation, because often when you're generating code in Kotlin, you need to make a compromise between what the API looks like from Kotlin and what the API looks like from Java. So like in the last case, you probably still want to provide that builder because it was a sane and clean API from Java. So you might end up like doing both, but it's something that you need to be aware of when you're generating code. But there are some other things that we kind of want to draw attention to, things that you might run into that could like hurt your generated code. So before, when we wanted this constructor property to be accessed as a field, we were easily able to add this annotation, and then you can, from Java, access it as a field. But if these were instead abstract properties, so for example, on an interface, then you can't do the same. You can't name the method that they're going to be calling from Java or make it a field. So you're always going to be calling getSwamp in this case. And yeah, so that's what's going on here. You always have this method signature.
Kotlin has a language feature called Reified Types that work in conjunction with another language feature called inline functions. And the way that this works is very specific to using these functions in Kotlin. It allows you to call this method passing in a type, and then the body of that method can actually has access to the class that's supplied. Unfortunately, if you use this in Kotlin or you generate code that uses this pattern, Java consumers are not going to be able to use it. The method that gets generated actually winds up being private. And so to work around this, you just need to be mindful of the fact that there are consumers in both languages. And so for Java, you should be supplying that explicit version of this method that actually takes a Java lang class. And here we've created some redundancy in the code, so there's still tricks you can do, like using one of the methods as the canonical one and just having the one that provides nicer Kotlin syntax call into it.
Now, the thing you should be worried about are these single abstract method interfaces. So in this case, we're adding a listener to listen to swamp changes. From Java, if you're using a single abstract method, then typically you might have this inner anonymous class that implements it, but the language can optimize it away into a Lambda, which is a lot nicer. Unfortunately, the same doesn't work for Kotlin. So you can't take this and instead use a Lambda for it. What Kotlin wants you to do instead is to ask for the Lambda directly. And so when you do this, now the API looks like what you want. You're accepting a Lambda instead of the object. But the Java side of it doesn't look as good. Now you have to sort of return this unit instance because it's required by all Kotlin Lambdas. Also, if you wanted to split this out, you wouldn't be able to name the interface. Like before, we could put it in a field and it would be swamp changed listener, but now it's just like function one. But so there is a workaround for this, which is where you declare the interface in Java and the API in Kotlin. And if you do this, then from Kotlin, you can do this SAM conversion where you just pass the type in addition to the Lambda, and it works fine. And then from Java, it's exactly what you would expect.
OK, so extension functions, again, another feature of Kotlin that enables really elegant extension of existing APIs. And where these are normally defined are on the top level of a class. And so here I'm adding a function to any nullable type to turn it into an optional type. Now, from the Java consuming side, this extension function is actually going to be placed in a separate class whose name reflects the name of the file. So if this was defined in an optional.kt file, the class that this function would be moved to and therefore consumed from in Java would be called optional.kt, which is not a very idiomatic naming. We can actually control this with file level annotation, and we actually can change the name of the function when it's exposed to Java to take into account the different ways that you call the method. In Java, we would be calling the method name and then passing the argument, whereas in Kotlin, we have the argument we want to operate on, and then we call the method after. And so we can control the names in both languages. But we're the one writing this optional class, and it's a little awkward to have helper methods for that optional class being defined on a second class, which is named slightly differently. What we would want is to have that method turn into a static method on the optional class when we're consuming it from Java. Now this works, but the problem is we've actually now broken consumers in Kotlin. The IDE is unable to find and resolve this extension method when it's defined inside the optional class unless you explicitly import it yourself. And so, we define this extension method to make the Kotlin experience more natural, and we end up making it worse by moving it inside the class to make it feel better in Java. Now, there's tricks for this, like you can do both. And again, this is similar to the Reified Types thing, where you just do what's right for Kotlin and what's right for Java. And there's a little hack where you can hide the extension method from Java altogether so that they don't see two versions of the same thing by using a class name that starts with a dash. And that's only valid in bytecode, not valid in the Java language. And so the IDE just ignores it.
So another thing to be wary of is if you're exposing the nothing type. Nothing is something that's like the subtype of all other types in Kotlin. You probably won't end up exposing it. But if you do, then from the Java side, if you're exposing just nothing, it gets turned into void. And if you're exposing a collection of nothing, then it just gets turned into the raw type. So in this case, list.
So we've been talking about code generation in sort of an abstract way up until now, just general principles. And I want to move into talking about a library called KotlinPoet, which is a library we published at Square. And what this allows is modeling code in order to facilitate code generation. And so to start with, the most important thing to know about KotlinPoet is how it models types. And so types exist in a hierarchy, like every class is a type. And you also can have things like parameterized types, which are also a type. And these represent things like string or map. So KotlinPoet actually models these types. And the reason it does that is so that it can, when you're generating code, it can automatically handle imports for you. And it can make sure that if you're referencing two classes with the same simple name, that in one of the cases, it'll actually emit the fully qualified class name to disambiguate. So KotlinPoet offers extension functions on things like K-class instances here. And when we ultimately use this and emit code that references this type, we'll automatically get an import for the fully qualified class name, but where you use it in the code, we'll only use the short name. And CollinPoet understands how Kotlin itself does resolution of these types. And so if you have another class called string as a sibling, CollinPoet understands that it can still use the short form, and it'll actually still resolve to the Kotlin string. But if you're defining this property inside the string class, and you want to refer to Kotlin string inside of it, it actually knows to omit the fully qualified class name instead of shortening it to just string where it resolves to the wrong type. So this is the motivation behind why KotlinPoet models types, is so that you don't have to think about this resolution stuff. As long as you're modeling types in the way that KotlinPoet expects, it will take care of that for you. And so we have ways to, so this was just a simple class. It also has ways to model parameterized types. And since Kotlin puts nullability into the type system, KotlinPoet also models nullability. Okay, to do code generation, we have these things called specs, and they're associated with the constructs of the language. And so if we want to generate a property, we have a property spec. And so I talked about how important classes are and how KotlinPoet models them, but most of the APIs we expose actually offer helper methods where you don't have to do that explicit as class name call. You can just pass in the class name, and it'll do it for you. And then KotlinPoet only models the higher level syntax of the language. It doesn't actually model like what's inside of method bodies or initializers. And so those are mostly strings, but you can use some string formatting helpers to refer to things. So in this case, I'm using $S and I'm emitting the string foo. And what I'm saying is I want this string that I'm passing in to be turned into a string literal in the generated code. And where this is great is if you're consuming code from a config file or parsing it from something else where there may be unprintable characters or special characters. And so if I parse this code and it has like a tab character, I don't want to actually emit a tab in the generated code. I want to emit a string that represents the tab. And so it will automatically escape control things like this. And you'll notice here that we get a fully qualified reference to string, Kotlin.string, instead of the shorter string. And I talked about how KotlinPoet does imports. And the reason behind this is because we're only modeling a property now, and there's nowhere for imports to live in a property. Imports live in a file, and so only when you actually wrap stuff up into a file spec do you get the imports and the package name handled for you. So for the rest of the KotlinPoet section, I'm just going to assume that you're going to put these in files. And so we'll look at the code as if it was generated like that. So aside from property specs, there's a few other specs for different language constructs. If we want to model functions, we have a function spec. If you want to model types and classes, interfaces, we have a type spec.
Yeah, and the interesting thing about this is that we're generating something that actually won't compile. And this was a philosophical decision from KotlinPoet, is that we are going to generate code for you, even if it won't compile, and instead lean on Kotlin C to fail when you try and run this code. So to actually make this work, what we want is the constructor property. So we need to add a few things to the code that we're writing here. The first thing is the property itself. Then you need to add a constructor parameter. And then still this wouldn't compile because you need to set name to something, in this case, the constructor parameter. So we add the initialization for it. And the interesting thing here is that now KotlinPoet has optimized the code you've written to instead use this constructor property syntax. And we do this for a reason. It's so that if you want to make changes later to how it's initialized, the change in your KotlinPoet code is very simple. And if in the future Kotlin introduced like some new language optimizations, we could easily add those in, and it wouldn't actually change the API on KollinPoet's side. We would do those optimizations for you when we generate the code.
Another place that you see this being done is with expression bodies for functions. And so here at the top, the code we're generating has a single statement, which is return and then a method call. But in the generated code down below, there is no return and there is no body to the function. We just use this shorthand syntax. And again, if you in the future change this code to add, say, a second statement, KotlinPoet will then desugar that syntax into the full regular function body with two statements and the actual return declaration. And so the whole point is that you write the code as if you write kind of the dumb literal code that you mean, and then if there's any more optimal syntax that we can generate, the tool will take care of it for you.
So one of the other things that you might want to do when you're generating code, and in this case we're generating some function, we're probably going to end up using it later. So one of the great things about CollinPoet is that you store the actual function spec into some field and you can reuse it later. So if we wanted to call the method later in generated code, instead of storing the name of the function somewhere, we can actually just reference the function directly. In this case, we're using this %n syntax, similar to what we were doing before when we wanted to pass a string. This will take a spec, and now the generated code is going to use the name for it. And this is great because if you come back and you want to change the name of a method, you only have to do it in one location, and then the generated code is going to reflect that everywhere because you used the one reference to the function spec.
So up until now, when we've been showing the code of the function bodies, we've been using this add statement function. And that's actually just a helper for this thing called a code block. And a code block is what models all of the interesting bits inside of functions or inside of property initializers. And so here's where we can do things like, again, add a statement. And you see we have $%t, and we're passing in a type reference. Again, this will do the right thing where it wraps it into the type that KotlinPoet understands. You wouldn't want to, however, replace this with int.maxValue, because then if you happen to generate a class called int in the same file, it would resolve to the wrong thing. So again, it's really important to use real types. And what's nice about a code block is that it allows you to use things like control flow in your generating code to actually control what's being generated. And so in this case, I'm modeling something, an enum with a yes or no value, and I can control the generated code as a result of that. And if you actually want to generate control flow, like if statements or when blocks, there's some helper methods for you which take care of curly braces, takes care of automatically indenting the generated code. So really, you only have to focus on what is being generated and focus less on actual how it's being formatted. Also, if these code blocks don't have to be things that can compile. And what's great is you can use them as references to things, to different constructs that you want to generate, and you can potentially pull them in from a bunch of different places, and then say use all of those as arguments to call a method. So in this case, I might pull arguments from 4 different places, and then I want to collapse them all together to emit like a call to a function.
These have all been pretty simple examples of what you can do with KotlinPoet, but what happens when we take this super contrived method signature and try and use KotlinPoet to generate it? Will it work? Of course, in this case, it does. So we're able to do everything that you might expect of Kotlin's rich feature set. Interestingly, when Jake and I were going over this slide, I asked, would you be able to name the Lambda parameter? And you couldn't, so we went to GitHub and we filed an issue on KotlinPoet. And then the next day, I woke up to a PR from Igor, who's one of the library maintainers, which was already fixing it. So it's ready to use. KotlinPoet is perfectly functional, but if it is missing features or has some bug, then you can file an issue and we're going to address it pretty quickly.
So up until now, we've been talking about generating Kotlin code and making sure that it feels idiomatic in Kotlin and also potentially from Java. But there's actually some other interoperability options that we have. So for example, if you are generating Java code already with an existing tool, there are things you can do to make the experience nicer from Kotlin. So for example, in this case, we have a method that returns a string. We annotate it with nullable because Kotlin models nullability in its type system. And it also has a name that's very standard in Java, the bean naming convention, where it's prefixed with get. And so if we're consuming this from Kotlin, we get to use the nice property syntax, and we get the nullability in the type system. OK, and so far we've been talking about code generation where you're generating source files, either Kotlin or Java, and then those are being compiled by some build tool into bytecode. We actually could skip this step and just go directly to bytecode, which is interesting. And you may actually already be the reason you might want to do this is that you already have bytecode transformations in your build step. It makes sense to potentially do some additional transformations in there to make this interoperability story even better.
So let's get into that. Let's see if we wanted to generate bytecode ourselves instead of generating the source files, what would it look like? To begin, we're going to go the other way around and look at the class file that's going to be generated. So for this case, we're going to go back to that abstract property that's defined on an interface. So if you use Kotlin to compile this and it gives you a class file, you could use a tool in IntelliJ, show Kotlin bytecode, to open up this file, and it will instead show you the class file in the editor in a way that's readable. And so if you do that, you're going to get something that looks like this. So there's a few things to note here. There's the actual Java method, the getter that's backing the property, which is getBar. And then there's this Kotlin metadata annotation. And this is the thing that really makes Kotlin tick. So all of those features that aren't in Java, like the nullability, default parameters, those are all being stored in this one annotation so that when Kotlin reads this file, it knows how to deal with those things like named parameters. If you're particularly interested in the metadata annotation and want more, there's a great talk from Eugenio Marletti that he gave at Kotlin Berlin Night, where he goes in depth on what each of the things inside of it mean, as well as like how you would parse it. Thankfully, he made a library that does this for you, so we're going to take advantage of that to get deeper into the metadata annotation and figure out what's going on. So we'll run some code, and we'll pass the annotation into his library to get back this proto, which is the Java object that has all the information in it. And the first thing I want to draw our attention to is this list of strings, which is essentially just a list of identifiers that are going to be used later in the proto. So now we want to kind of find the property inside this object. So if you do some digging, you can find this property type. And inside there are a bunch of fields. The one we care about is the name field. And you can see right now it's an integer. That is the index into the string identifier list that we saw from earlier. So in this case, the name being 2, what that means is that we're using the identifier at index 2 of the strings array here. So it's called bar. The property is called bar, which makes sense because that's what we defined it as in the file. The other thing that we care about is the getter method that's backing the property. So again, looking through the proto, we can find that field and all of the attributes with it. And in this case, again, what we care about is the name of that property getter backer. And in this case, it's 4, which going back to our string array, index 4 is getBar, which makes sense. So the property is being backed by the method getBar. So theoretically, if we wanted to change the name of this method, we would need to make 2 changes. We would need to change the name of the actual method itself at the top there. And then in the metadata, we need to change the name of the method that's backing the property, which is stored there. So now if we want to generate the bytecode ourselves with those changes, we're going to need a new tool. And it's called ASM. This is what Kotlin itself uses to generate bytecode, and a lot of bytecode transformers use, like Spring or Hibernate. And it's what's going to help us write bytecode. The thing that's great about it is that it works in both directions. So you can pass it Java bytecode, and it will give you back the Java code that generates it. And then, of course, that Java code is using ASM to generate the bytecode. So if we take our class file and now pass it into ASM, it's going to give us back all of the Java code that generates that class file. And I've taken a snippet here, and these are the 2 things that we wanted to change in our class file. The bottom one is the method name of the Java getBar, and the top one is in the metadata annotation, the string identifier list. One thing that's important to note here, if you're writing bytecode for Kotlin and want to generate that Kotlin metadata annotation, don't do it this way. What you should be doing is making changes to the actual proto, the thing that Eugenio's library was giving us back, and then serializing that into an annotation, instead of just like sort of hard coding the annotation itself. And that's so that you can maintain compatibility with Kotlin itself. So we make our 2 changes here that we want in the bytecode, changing the method name to bar in both the string array as well as the method itself. And now we pass that back into ASM and get our generated class file back. And now we get the thing we want. If from Java we implement this interface, the implementation method is just called bar. And from Kotlin, the property is just called bar. This is like sort of hacking around Kotlin. And in fact, if you opened up the IDE, it would have a lot of red in it because it doesn't understand what we've done to the class file. But this compiles fine if you're just doing it from the command line.
Yeah, so there's other reasons that you might want to dive into doing some of this manipulation in bytecode. One of the reasons is that if you have a fairly large, maybe fairly popular SDK written in Java for a popular mobile platform that has a method defined like this, if you call this in Kotlin, it's not really a great experience. We have no idea what these parameters mean. We have no idea which corresponding side of, in this case, the rectangle that they correspond to. What we want is something like this, where we can use the features that are in the language to make it declarative as to which side we want, and also use the fact that we can have default values for the sides that we don't specify. And so if you have something that's already written in Java and being compiled to Java bytecode, you have the potential for going in and mixing in this metadata so that when that file is consumed then from Kotlin, you get a much more idiomatic experience, an experience of calling the method as if it were written in Kotlin.
So you can gain these Kotlin-like features either by generating the Kotlin code or perhaps adding the metadata annotation explicitly yourself in the bytecode. So you might be wondering, is there actually a reason that you would want to generate the Kotlin source file instead of bytecode? Obviously, it's a lot cleaner, so that's what you should be doing. But is there anything that you wouldn't be able to do if you were generating the bytecode yourself? And the answer for this is multiplatform. Multiplatform support for Kotlin is one of the biggest selling features of the actual language. And for code generation, I think it's particularly interesting because when we were talking about the different ways that you're generating Kotlin code, you're going from things that are not platform specific. So something like a proto file, a SQL file, those ASTs, none of those are tied to a specific platform. And in fact, we ran into this at Square on Cache because we use a proto file to describe the requests and response that are happening for all the clients. And for server and Android, that's great because we have Wire, which generates that Java type for us. But for Objective-C and for JavaScript, they don't have that kind of solution. So they're doing something different. And it would be great if we were able to share the tool chain that we're using to parse the proto file. And so that's exactly what you can do by generating Kotlin. You'll get something that works on JVM bytecode, JavaScript, as well as LLVM or native, pretty much anything that's running native.
Yeah, so there's a lot of important rules when you want to change from generating Kotlin code that's specific to one platform to generating Kotlin code that has the potential to work on these multiple platforms. And so currently KotlinPoet is written in Kotlin, but it requires that it's run on the JVM. And that means then the tool that you write, which is consuming KotlinPoet, also runs on the JVM. And so this means we're interacting with the Java APIs as we're writing the tool. And so it's very easy to accidentally slip in things like a reference to a type that you're used to using every day when targeting the JVM. But this is actually a JDK-specific type. And so if we want our generated code to run on multiple platforms, we can't do this. We have to be extremely mindful of this. And really, this comes down to just testing infrastructure. We have a tendency, because KotlinPoet only runs on the JVM, to therefore only run your tests on the JVM. And what you really need is for the generated code to be tested on every single platform that you're targeting, because then this just won't compile and you'll be able to catch it. Platform types are inherently useful when you're actually only targeting a specific platform. And so the rule here is that if you're generating code from some other code, if the user themselves references a platform type or a library type that's specific to one platform, then you're allowed to reference it in the generated code. So in this case, I have some fictional code generator based on an annotation. And because the user who wrote this code used Guava's immutable list in the property, as a code generator, I can see that type and then generate code which also uses it because they did it first. And this is also true for if you're not starting from code. We have a library and tool called SQLDelight, which adds type information to SQL. And in this case, if the person who wrote this snippet referenced a Android-specific type in the SQL file, then as the code generator, we're also allowed to now reference it because we know that if the user referenced it, they intend to use it on that platform. And we don't have to worry about referencing something that's platform-specific because, again, they did it first. Since you don't know the target platform of generated code, or at least you should try and be agnostic to the target platform, it's extremely helpful if the code you generate feels nice, regardless of what platform it's being consumed on. And so we have these annotations that allow you to change the name of a method or function based on what language it's being called from, because the way you call it is different. And so from Kotlin, we get the extension function, and from Java, we get the static method where the argument comes after. And so we might want to change the name. Unfortunately, currently, we cannot actually include these annotations in generated code if we want the ability to target multiple platforms. The JVM name annotation is actually in the standard library that you would use for writing multi-platform code, but when you try and compile it for JavaScript, they actually made the annotation internal, and so it fails to build. Similarly, if we want to change the name for consumers from JavaScript, there is a JS name annotation normally, but if you're using the multi-platform standard library, it actually doesn't exist at all. And so we don't have the ability to yet target each of these platforms with more idiomatic naming. And you may not have noticed, but there are bugs filed for all of these things. So hopefully in the future, this limitation for generated code will actually go away.
Okay, so as a summary of the things that you might want to keep in mind when you're generating Kotlin code, the first and I think most important thing is that verbosity is okay. So it's fine to generate those equals hashcode and 2 string methods. The thing that matters is API. And in addition to that, it's API from Java as well as from Kotlin. And so if you do any Java code gen instead of Kotlin code gen, it's still important to keep in mind Kotlin consumers and following the Interop guidelines for both languages. And finally, don't depend on any platform types in your generated code. Make sure that they're things that are being supplied to you from the user instead of you exposing that dependency on a platform yourself.
So on Friday, we released a new version of KotlinPoet, the KotlinPoet library. We are pretty confident in the types of Kotlin that it can generate. There still are some things we're finding, but it's extremely usable now and today. And we would love for you to, if you're doing code generation, give it a try and see if there's anything it can't do. It is pre 1.0, and the reason for this is that we also have a library called Java Poet for doing code generation for Java. And Kotlin Poet was basically forked from that and then changed to generate Kotlin. And so its API feels very Java-y. And we, in the future, might want to change that to take advantage of, again, some of the syntax in Kotlin, like DSLs. But the important thing is the code that it can generate. And we really want to make sure that it's able to generate anything and everything that you would want. And so if you are doing code generation, please give it a try.
Sweet. And that's it. Thanks a lot.
Thanks.